Thank you for joining our presentation. I'm Zhifeng Zhang. I'm the corresponding author and presenter today. The topic we are presenting today is called Electrolyzer Degradation Power Electronics One-Way Interaction Model. In this work, we develop a numerical model to study the influence of electrolyzer degradation on the performance of power electronics. This work is a collaboration between UQTR and Air Liquide. Before the presentation, I would like to briefly introduce our Air Liquide Research Center at Newark, Delaware. Our center locates at the Greater Philadelphia area. Here we have 7 laboratories and 6 experimental platforms. The work presented here is conducted by the Process Engineering and Combustion Group. In the Process Engineering and Combustion Group, they focus on CO2 capture, combustion, and hydrogen technology. Here's the outline I'm going to present. First, I'll give an introduction about our project and research objectives. Then I'll move on to technical approach, results, and conclusions. As a background, Air Liquide operates the world's largest PEM electrolyzer to produce hydrogen at Quebec, QC, Canada. Different from traditional chemical plant. You can see here we have less chimneys. And in this plant, we produce 100% green hydrogen with 0 carbon emissions. And our collaborator UQTR is about 20 miles away from our plant. Talking about water electrolysis. On the left side, the picture shows the number of publications before the year 2020. As we can see, since about 1970s, the number of publications per 5 years increased exponentially. Recently, the power of electrolyzers has reached a megawatt scale. On the right side picture, we summarize the megawatt scale PEM electrolyzer development with years since 2018. The x-axis is the years, the y-axis is a megawatt scale. As we can see, since 2018, the development of electrolyzer power also increased exponentially. Our 20 megawatt PEM electrolyzer in Bécancour has been the biggest since 2021, and now you can see there are several other bigger electrolyzers under construction. And by the year 2025, the biggest reported electrolyzer is the electrolyzer in Normandy, France. On the left side is a picture of our 20 megawatt Bécancour plant. This plant has 4 units. Each unit is 5 megawatts. And in this process, Air Liquide buys energy from Hydro-Quebec. Through our water electrolysis process, we produce hydrogen for our customer. In this process, power electronics plays an important role to stabilize the whole system and converting the high voltage AC to low voltage DC. The cost of power electronics usually takes about 15 to 20% of the whole system. And the capex basically decided by the topology of the converters, such as whether it's direct based or IGBT based. Air Liquide is more interested in the OPEX part, how to minimize the wasted electricity, how to improve the power quality and decrease the ripple. More specifically, in this project, we are interested in the whole system performance and the long-term operation, especially under electrolyzer degradation. Some recent study shows power electronics plays an important role on electrolyzer lifetime. One result shows that this ripple will generate PEM degradation, and thus a shorter PEM lifetime. Also, the bigger ripple factor will accelerate this process. Then another study shows power electronics especially converter topology, can reduce specific energy consumption very significantly. Then based on these results, one question we are interested in is, with the degradation of electrolyzer, whether power electronics can accelerate or decelerate the degradation of PEM electrolyzer. Then to answer this question, we built an electrolyzer degradation power electronics model. And in this model, we can study the electrolyzer degradation influence on power electronics to study the power factor in the AC side and the ripple factor in DC side. Here is the technical approach of our research. We first built a MATLAB Simulink model to simulate the whole water electrolysis process, including the main grid, power transformer, rectifier, electrolyzer, as well as the control part. Then we simulate the PEM electrolyzer as a resistance. Then based on the degradation knowledge, we understand the degradation rate for electrolyzer is between 1% to 4%. Then we add a dynamic resistance to the numerical model. That means in our model, we have a constant degradation rate between 1% as a very ideal case, 4% as a very, very bad case. Based on the dynamic resistance, we can study the system performance, including the voltage output, DC ripple, and power quality. Our result is for constant current condition. That means we assume the system produces the same amount of hydrogen with time. On the left side is a performance system for 2% degradation rate electrolyzer. And we can study the performance up to 10 years. Then in this study, we are interested in the output voltage, ripple profile, and ripple factor. As we can see with the operation time, the DC voltage increase. That means to produce the same amount of hydrogen, we need to pay more. But at the same time, we can see actually the ripple in the process is not increasing, but decreasing. This is kind of counterintuitive. That means with the degradation of the system in 10 years, the whole system performance decreased, but the power electronics quality, the performance increased. And also for 1% degradation rate system on the right side, a similar conclusion can be obtained, but we can see actually the ripple factor decrease is not as significant as 2%. At the same time, we studied this ripple behavior under different load, from 20%, 60% to 100%. As we can see, for both 2% and 1% case, the ripple factor decreases with time. Since our current PEM system is using 6-pulse diarrester, then we compared a different technology using the IGBT topology. As we can see on the right side, at the same degradation rate, the change of ripples actually is less significant for the IGBT technology. That means the IGBT technology is more stable than the 6-pulse diarrester under degradation. For the AC side, we conducted the same research for power factors. As we can see for the 2% degradation rate system, the power factor for the 6-pulse diarrester or our current system is increasing. But for the IGBT technology, actually there is a trend of decreasing. For the AC side, we studied the total harmonic distortion for different topologies as well. As we can see, the total harmonic distortion for the current 6-pulse diarrester has a going down trend. This also happens for the IGBT technology. After simulation, we validated our model using the test results from Beacon-core plant. In the validation study, we validated two cases. One is for the short-term 1-hour operation, another is for long-term 4-month operation, but both are at 20% load cases. As we can see, for both cases, the simulation results and the test results, they match pretty well. However, due to the limitation of our plant, we can only measure power factor, not ripple and THDs. That's the work we are going to do in the future. Here comes the conclusion part. In this study, we built a one-way interaction model to study the influence of electrolyzer degradation on power electronics performance. Then for our Beacon-core plant, all power electronics evaluation parameters, including the DC ripple, AC power factor, and THD, all these parameters are improved with the electrolyzer degradation. This result is counterintuitive. It means with the degradation of electrolyzer, the whole plant performance becomes worse. However, the power electronics performance is not decreased but increased. At this moment, we are still investigating the physics behind. In our other studies, we compared it with different topologies, and this phenomenon is less significant for IGBT, and we conclude IGBT is more stable. At the same time, we only partially validated our simulation result. We are still working on validating other results. Here are some references we use in this study, including our last series work and some other one-way interaction models. Finally, I would like to thank the support of MITAB on this project. Also, we would like to acknowledge support of American Air Liquide and Air Liquide Canada for the permission to publish the work. At the same time, we thank the input of our colleagues who commented on this draft. Finally, together with my co-author Mohammed and Marcos, we would like to respond to your questions, comments. And also, I would like to say at the Innovation Campus Delaware Air Liquide, we are interested in all kinds of hydrogen projects. So if you would like to work together with us, please contact us. Thank you.